Okay, yeah. Okay, hi, I'm Nick Mosier. I'm a PhD student at Stanford, advised by Trippel, and I'll be presenting on how we're using hardware-software co-design to develop efficient mitigations for Spectre. So Spectre attacks are a type of hardware side channel attack. In these attacks, a victim program running on vulnerable hardware leaks secrets that it processes to an attacker. Specifically, the victim executes what are called unsafe instructions, which are called transmitters, whose execution creates operand-dependent hardware resource usage. An attacker then infers the values of the transmitter's sensitive operand by measuring hardware resource usage through execution time or other means. So a classic example of a transmitter is a memory instruction, like the load on this slide, which modifies cache state as a function of its address operand. An attacker can measure this address-dependent cache usage by timing its own memory accesses, which contend for cache resources in the victim. So Spectre attacks are a particular kind of hardware side channel attack, which exploit transient execution due to control flow or data flow mispredictions in hardware to steer secrets towards the sensitive operands of transmitters. So by transient execution, I mean the execution of instructions that never architecturally commit. So basically they're rolled back due to a prior misprediction. And so on this slide, I'm just showing a vanilla Spectre attack that exploits conditional branch misprediction. This is basically the first Spectre variant, one of the first Spectre variants to be disclosed. So the two lines in gray here are transiently executed instructions due to the branch misprediction. Line 2 is a out-of-bounds array access due to the misprediction, which can return a secret, which is then leaked via by passing it to an address operand of the array access on line 3. So in general, Spectre attacks are Spectre attacks pose a unique and complex security challenge, and that's because speculative execution is critical for the performance of modern processor performance. So you can't just disable it. But on the other hand, Spectre circumvents many of the protections offered by well-established secure programming paradigms. So for example, it can coerce a constant time crypto library like OpenSSL to leak its private keys. It can coerce the Linux kernel to leak arbitrary memory of other processes, or it could allow sandbox WebAssembly code to break out of its sandbox and leak host data. So on modern processors, there are 5 well-documented sources of mispredictions that enable Spectre. These are called speculation primitives. So on the control flow side, we have conditional branch prediction, which we already saw, or PHT. We also have indirect branch prediction, which can cause an indirect jump to speculatively jump to any instruction in memory. It's shortened to BTB. And we also have return address prediction, or RSP, which can cause a return to the wrong call site in the program. And so on the data flow side, we have store-to-load forwarding prediction, or STL, by which a load may speculatively read from any prior same address store, and predictive store forwarding, or PSF, which can additionally cause a load to read from any prior different address store. So Spectre attacks can leverage any combination of these 5 speculation primitives. And so that makes it's really challenging to comprehensively mitigate Spectre. And so here's, existing mitigations can be roughly grouped into 3 categories here, shown in this table. So first, there are unimplemented hardware mitigations. These generally seek to comprehensively mitigate Spectre. And they also have the benefit of requiring little to no software cooperation. But they haven't been deployed in practice, and this is likely due to the complexity of the hardware changes they require. So second, there are the hardware mitigations that have actually been implemented by hardware vendors like Intel. These are generally just speculation controls that allow software to entirely disable a speculation primitive for a particular process. But they're rarely used in practice because of their high overhead, and they don't protect against all speculation primitives like PHT, conditional branch prediction. And so finally, we have the software-only mitigations, which aim to target existing hardware. But none of these are comprehensive for any threat model, and Only one has been widely deployed that we know of, Reptiline, which tries to protect against Spectre BTB, but in doing so introduces other Spectre vulnerabilities. And so the result is that even the most secure deployable Spectre mitigation doesn't protect against some speculation primitives and has unacceptably high overhead. So as a result of this, many major security critical applications forgo these proposed mitigations and just remain insecure. So for example, last year OpenSSL came out with this blog post that confirmed OpenSSL contains Spectre vulnerabilities, but later said that they're not going to, don't plan to deploy patches due to the difficulties in comprehensively mitigating it. Linux does try to mitigate some variants of Spectre, but they, at least for Spectre PHT, they resort to manual source mitigations, which are incomplete and admit themselves that they are likely missing many instances of Spectre. And so, as a result, with this in perspective, our goal is to develop a comprehensive, efficient, and low complexity Spectre mitigation that can be widely deployed in security critical applications like OpenSSL and Linux with negligible runtime cost. And the way that we think, the best way to do this, we think, is using precise software analyses at compile time to be able to precisely pinpoint programs and mitigation requirements, and then communicate that to hardware. But these analyses face this approach faces three major problems, which we'll need to overcome first. So first, unconstrained speculative control and data flow. Second, weaknesses in existing programming contracts. And finally, a lack of fine-grained mitigation primitives. And the solution, though, we think, is to engage in hardware-software compiler co-design. And we think that we can basically solve all three of these problems with this approach. And for the rest of this presentation, I'll show how we've overcome the first two problems, or provided preliminary solutions to the first two problems in our mitigation Serberus. So Serberus is a first step towards our overarching goal. It is a comprehensive and proven correct software mitigation for constant time code that targets existing hardware. So first let me just say, our notion of, when I say constant time, we mean something slightly different. We mean more data oblivious code. That's a term that's also being used recently, as in, not in that the program is always going to execute in the same amount of time, but that its execution time simply doesn't depend on secret values. And so it's a bit different of a notion than the last presentation. So basically how Serberus works is its goal is to allow secure speculation for these first four speculation primitives, and it just disables the last one, PSF, for performance reasons. Basically, in order to do these precise analyses that I was talking about the last slide, we need to solve some of the problems. And so we have two co-design supports to do this. So first, we design a new programming contract, and we also design some speculation constraints using features on existing hardware. Okay, so for the rest of this presentation, I'm going to talk about those two co-design supports, talk about some limitations of Serberus and how we're trying to overcome those through more hardware-software co-design. Okay, so first, constraining speculation. So Serberus relies on static analyses, but processors by default exhibit unconstrained speculative control and data flow, which makes it impossible to do this analysis. But our key insight is that we can constrain speculative control and data flow just enough using existing features on x86 processors to enable these analyses while exhibiting almost no runtime overhead. So specifically, we're using Intel CET, which restricts the control flow targets to special instructions in the program, and PSFD, which is a speculation control that only allows loads to read from prior same address stores. Okay, so now moving to the software side. So when we were designing Serberus, we realized that there were these two constant time code patterns, so basically legal constant time code patterns that violated the assumptions we wanted to make and that we needed to make to have an efficient mitigation. But it turns out both of these were inherently vulnerable to Spectre attacks anyway, so there's not good programming practices for constant time code. So the first one is latent constant time violations. These are legal in constant time just because they never non-speculatively execute due to an impossible condition. Second, we have passing secret arguments by value. So this is a bit more nuanced. This is insecure because function calls can often be mispredicted via Spectre and jump to the wrong function, which would then leak their secret arguments. This would mean that a software mitigation has to assume all the arguments can always be transiently secret, which often reduces to just inserting a speculation fence at the beginning of the function, which has a high overhead. So to resolve this issue, we propose a strengthening of constant time programming called static constant time programming. This prohibits both of these vulnerable patterns by requiring first static security types of variables, and second, forbidding passing secret arguments by value. Instead, you can pass them by reference. And so we did actually find some, while constant time code generally satisfies static constant time, we found some instances where it wasn't satisfied due to passing secrets by value. And these actually manifested as, potentially exploitable Spectre vulnerabilities. Okay, so now that we have both the speculation constraints and static constant time, we can develop this new notion of a taint primitive, which will help us pinpoint the source of Spectre leakage in constant time programs. So in contrast, prior work often attributes the source of Spectre leakage to these things called access instructions, which are simply loads that load secrets from memory into registers. But since constant time programs are allowed to access secrets, this abstraction doesn't really fit well with constant time programs. So instead, we define this new notion of a taint primitive, which basically describes when when some instruction introduces a secret value into a publicly typed register. And so we then formally prove using operational semantics that there exists exactly 4 kinds of taint primitives in programs that satisfy Serberus' speculation constraints, and hardware that satisfies Serberus' speculation constraints, and software that satisfies the static constant time programming contract. And we also prove that all Spectre leakage involves one of these taint primitives. So this basically inspires this is a strong result which allows us to design basically a new kind of mitigation that, rather than focusing on access instructions, focuses on taint primitives. So Serberus itself consists of these 3 passes on the slide, each of which we implemented in LLVM. And so each pass eliminates one class of taint primitives, and together they eliminate the final 4th class. So the first pass is fence insertion. I'll talk about that a bit later. The second pass is function private stacks. I don't have time to go into this detail. It's an interesting approach, but basically what it does is it assigns distinct physical stacks to each function in order to prevent Spectre leakage due to stack sharing. And so the final pass, called register cleaning, is pretty simple. It just zeroes out registers that may hold secrets at function exit. Okay, so here's a subset of the results for Serberus running on a variety of constant time crypto benchmarks, so including OpenSSL. So the y-axis represents runtime overhead compared to an insecure baseline. So Serberus outperformed both of the state-of-the-art mitigations despite offering stronger security guarantees. And we saw an average of only 6.4% overhead for the larger buffer benchmark, so they were processing larger buffers, like encrypting larger amounts of data. So one limitation, though, we noticed is Serberus' performance does not scale to other application domains. It seems to be well suited for constant time, but just doesn't work so well for other applications. And so, in fact, we ran it on the spec CPU benchmarks, and we saw over 300% overhead, so a huge difference. And so there are a couple different reasons for that. I can't go into all of them, but basically, we did notice that almost all the overhead was coming from the fence insertion pass, the one I haven't talked about yet. So I'll talk about it now. So this pass frames optimal speculation fence insertion as a min-cut problem over the transient control flow graph of each procedure. So first it constructs this graph. Then we identify a set of sourcing pairs where the sources are a subset of loads and stores that may access secrets, and sinks are dependent transmitters. We then use a min-cut algorithm to identify the set of transient control flow edges to remove using L fences. And then we insert those L fences into the program. So for crypto code, this works pretty well, but for more general purpose code, which contains more frequent branches, this often reduces to simply inserting an L fence after every branch, and therefore disabling branch prediction, which incurs the huge overhead. But really, this isn't a problem specific to Serberus. This is a symptom of a greater problem, which we call the coarse-grained mitigation problem. So software knows which instructions can be involved in a Spectre attack and knows where to precisely place those mitigations and under what conditions they should be enforced. Hardware, on the other hand, knows the exact runtime conditions and can selectively enforce those software-selected mitigations. But in between them is the ISA, and the ISA only offers heavyweight coarse-grained mitigation primitives like lvents, which installs the entire pipeline rather than individual instructions. And so in effect, no matter how precise we can make software analyses, almost all of that precision is lost when it's converted into these coarse-grained L fences when communicated to the hardware. And so this really reveals we think will be the biggest co-design area, which will be the development of fine-grained predicated mitigation primitives to expose through the ISA. So I'm not going to present on all of these primitives that we're actively working on to extend Serberus with, but I'm happy to talk about them offline though. For now, I'm just going to talk about this one called nospec. And so nospec is essentially just an instruction flag or instruction prefix that indicates the instruction should be delayed until it becomes non-speculative. And so what we're planning on doing is replacing the fence insertion pass with a nospec insertion pass, which basically intuitively just flags loads whose values may later leak. And what's nice about this is it does not block all speculation like the original L-fence insertion pass would for the example code here at least, and resulting in better performance. Okay, so that's just about the end. So briefly, the takeaways are, we think that hardware-software compiler Codesign is necessary for efficient Spectre mitigations. We've done some of that to develop Serberus, which works very well for constant time code, but doesn't work well for non-constant time code. So we're currently looking into extending Serberus with these fine-grained predicated mitigations. Our preliminary results show we're getting about 15% overhead. We think we can get less than that, so I think we'll get a huge speed up compared to the 300% we were seeing before. Okay, so thanks for listening. I'm happy to take any questions at the end of this block.
Thank you.